because there is so much content on this next test, we are going to spend 2 lessons reviewing for it. So the first thing we discussed were sequences. Remember, sequences are lists, whereas a series is a sum of the things in that list. To determine whether a sequence is convergent or divergent, find its limit. So we're going to find the limit as n goes to infinity of these a sub n's to n squared plus 1 over 3n squared plus 2. Technically, at this stage, what we do is we multiply by 1 over n squared, or divide both the numerator and denominator by n squared. That gives us the limit as n goes to infinity of 2 plus 1 over n squared over 3 plus 2 over n squared. So that limit is 2/3. So what we say then is that the sequence an converges to 2/3. Now, sometimes a lot of you get a value that is not 0 here and you say, oh, that means blah diverges. What you're confusing there is a sequence and a series. The sequence, or the list, converges to 2/3, but the sum of the things in that list diverges. So make sure that you can keep those 2 things straight. All right, how about this one? So, well, this looks a little bit like, if I just didn't have that sign there, I'd have n over n squared plus 1, which would pretty obviously go to 0 since the denominator's degree is larger than the numerator's. The technical way you prove this is using the squeeze theorem. You know that sign is in between -1 and 1. So we have that negative n over n squared plus 1. That's less than or equal to n times sine of n over n squared plus 1, which is less than or equal to n over n squared plus 1. And the limit as n goes to infinity of both positive negative n over n squared plus 1. Technically what you would do here is you would divide by n, which would give you the limit as n goes to infinity of 1 over n plus 1 over n. Well, that's going to be 0 in both cases. And so thus, the limit as n goes to infinity of n sine of n over n squared plus 1 is also equal to 0. The theorem used there is by the squeeze theorem. All right, ln of n over root n. So find the limit as n goes to infinity, natural log of n over root n. Well, this is an infinity over infinity limit, so we want to use L'Hopital's rule. So I'm going to change my n's to x's because L'Hopital's rule only applies to functions. And now we have an infinity over infinity limit. This is equal to the limit as x goes to infinity of 1 over x over 1/2 x to the negative 1/2. And before you go nuts and apply L'Hopital's rule again, let's try to simplify this and just check and hope that we don't have to. So that's the limit as x goes to infinity of 1 over x over 1 over 2 root x, which is the same thing as the limit as x goes to infinity 1 over x times 2 root x over 1. And then that simplifies to 2 over root x. And as x goes to infinity, this limit is 0. So you can say the sequence a sub n converges to 0. All right, so if we say that a sub n is n cubed over n squared plus 1, let's find the limit as n goes to infinity of these terms. And you might suspect that this should diverge because the degree of the numerator is greater than the denominator, and that is correct. The technical reason why is that at this stage you multiply by 1 over n squared. There's one way to show that. When you do this, you get the limit as n goes to infinity of n over 1 plus 1 over n squared. And that numerator is going to infinity, the denominator is going to 1, so this thing is going to infinity. And in that case, your sequence diverges. So one way a sequence can diverge is it can blow up by going to positive infinity or negative infinity. Another example of something that diverges but does not diverge by going to infinity is the sequence an, where an is negative 1 to the n. This is, starting at n equals 1, let's say, is the list negative 1, positive 1, negative 1, positive 1, etc. Those numbers, while they do remain bounded, never settle down and go to one place. So this thing also diverges. So, in summary, a sequence can diverge in more than one way. One way is that the limit's infinite, or one way is if you have some kind of pattern where the numbers don't settle down and go to one place. Now, the next unit we discussed was series, where you added up the terms in a sequence. So, the series that we have, so when I say to find the sum, the series, you know how to find the sums of our geometric series and telescoping series and certain Taylor or Maclaurin series. So this to me looks like it's geometric, but remember that the geometric series formula said that the sum from n equals 0 to infinity of ar to the n was a over 1 minus r if the absolute value of r was less than 1. And that formula depended upon the fact that that sum began at 0 and this one does not, so gotta do some reindexing. And before I go there, I'm also going to change this 2 to the 3n into 8 to the n. So negative 3 to the n minus 1 over 8 to the n. And that's because 2 to the 3n is the same thing as 2 to the third to the n, and 2 to the third is 8. Now we reindex and we let this equal a sum from n equals 0 to infinity. And that makes this 8 to the n plus 1, and this negative 3 to the n, which is the same thing as the sum from n equals 0 to infinity, negative 3 over 8 to the n times 1/8. So our a is an eighth, and our r is negative 3/8. And since the absolute value of negative 3/8 is less than 1, the series converges. And in this case, it converges to a over 1 minus r, so 1/8 over 1 minus negative 3/8. So that's 1/8 over 1 plus 3/8. Multiplying by 8, we have 1 over 8 plus 3, or the series converges to 1/11. Another series we could find the sum of exactly was a telescoping series, and one trick for a telescoping series was to use partial fractions. So 1 over n times n plus 2, well, that will be a over n plus b over n plus 2, or 1 must be equal to a times n plus 2 plus b times n. Inputting n equals 0, we find that 1 equals 2a, which means that a must equal a half. And inputting n equal -2, we get 1 equals -2b, which tells us that b must equal -1/2. So this series is the same thing as the sum from n equals 1 to infinity 1/2 over n minus 1/2 over n plus 2. And just to make this simpler, I'm going to take that 1/2 out. And I'll have 1/2 times the quantity sum 1 over n minus 1 over n plus 2. Now to find the sum of a telescoping series, you have to find an expression for the nth partial sum. So what do you get when you add up the first n things? So we have this 1/2 that's just going to hang out. Then we input some numbers and we hope for a cancellation pattern. So inputting 1, we have 1 minus 1/3. Inputting 2, we'll have 1/2 minus 1/4. Inputting 3, we'll have 1/3 minus 1/5. And you can see then that this -1/3 and that positive 1/3 are going to cancel. One more, plus 1/4 minus 1/6. And you see that, okay, this 1/4 and that 1/4 are going to cancel. The 1/2 won't cancel, and neither will the 1, but everything else will. Now on the tail end, the very, very last term you have will be 1 over n plus 2 minus 1 over n. One prior to that is 1 over n minus 1 minus 1 over n plus 1. And one prior to that is 1 over n minus 2 minus 1 over n. And you can see here, this 1 over n will cancel with this 1 over n. This 1 over n minus 1 will cancel as soon as we write another term down. So in this case, the only terms left are the 1 plus the 1/2 from the beginning, and the -1 over n plus 1, and the -1 over n plus 2 from the end. So this Sn tells you what you get if you were to sum up the first n things, like first 100, first 1,000, first million. Now the infinite sum, so we'll say call that S, will equal the limit as n goes to infinity of this Sn. And as n goes to infinity, this term will go to 0 and this term will go to 0. And so this limit will be 1/2 times 3/2 or 3/4. So in that case, that infinite series sums up to 3/4. Another important test you had in this first unit where we just began to discuss series was the test for divergence. And if you see a series and you're kind of clueless as to what to do with it, find the limit as n goes to infinity of the terms. And if that limit is not equal to 0, then you know that that series diverges. If the limit is 0, then it's inconclusive. The series could converge or diverge, you just don't know. But if it's not 0, then the series will have to diverge. So for this one, find the limit as n goes to infinity of natural log of n over 3n plus 1. Well, that limit can move inside the natural log because natural log is a continuous function. And as n goes to infinity, n over 3n plus 1 will go to 1/3. And ln of 1/3 is not equal to 0. So thus the series diverges by the test for divergence. The next test we had was the integral test. So this is used when you have a function or things inside of your series for which an integral would probably be possible, and things like the ratio test fail. Now, to use the integral test, we're going to define a function f of x that matches the terms of your series. And f of x has to be three things. F of x must be continuous, it must be positive, and it must be decreasing. And in this case, we care about the interval from 2 to infinity. And so remember that you can say a function is obviously decreasing if you only have variables in the denominator. If there's variables in the numerator and denominator, you have to use a derivative to prove that the function is decreasing. So state that you understand that you're using these three things, because the proof of this test relied on these three things. And if you have a function for which this is true, then what this gives you is that the integral and the series will do the same thing. So instead of finding the sum, you can find the integral from 2 to infinity, 1 over x square root ln of x. So that's the limit as b goes to infinity, integrate from 2 to b, 1 over x root ln of x dx. And we'll do a u substitution for ln x. Du will be 1 over x dx. You also need to change your bounds. If x equals 2, u will equal ln of 2. And if x equals b, u is equal to ln of b. So our integral is a limit as b goes to infinity, integral from ln of 2 to ln of b, u to the negative 1/2 du. All right, the antiderivative of u to the negative 1/2 is 2u to the positive 1/2. So that's the limit as b goes to infinity, 2 root ln of b minus 2 root ln of 2. And as b goes to infinity, natural log of b goes to infinity, so does square root of it. So this is going to go to infinity. And so as the improper integral diverges, so does the series. One thing the integral test was used for was to prove that p-series converge, when a series that is a p-series converges or diverges. And so this is an example of such a p-series. This is the sum from n equals 1 to infinity, 1 over n to the 3/5. And this is a p-series with p equal to 3/5. And as 3/5 is less than 1, this series diverges. But my point is if you forgot that about p-series, you could apply the integral test to prove that this series diverges. So another good thing about the integral test is that it gave us a means to estimate series. So let's estimate this using S5. So S5 would equal 1 over 1 plus 1 over 2 to the 6 plus 1 over 3 to the 6 plus 1 over 4 to the 6 plus 1 over 5 to the 6, which is approximately 1.0173. And the integral test said that the error, or the remainder, if we leave off the first 5 terms, was less than or equal to the integral from 5 to infinity of 1 over x to the 6th dx. So that's the integral from 5 to infinity x to the negative 6th dx. So that's a limit as sum b goes to infinity, integral from 5 to b, x to the negative 6th dx. So that antiderivative of x to the negative 6th is x to the negative 5 over negative 5, evaluated from 5 to b. So that will be negative 1 over 5b to the 5th plus 1 over 5 times 5 to the 5th, Well, as b goes to infinity, that first term goes to 0, giving us 1 over 5 to the 6th power as an upper bound for the remainder. Now the next tests we had were the comparison tests. We have the direct comparison test, and we have the limit comparison test. Okay, and both of these tests you have to have a series with positive terms. All right, this looks a lot like the series 1 over n cubed. So can we establish direct comparison? So if you want to show this series converges, it has to be smaller than something that you know converges. So, well, n cubed plus 1, that's bigger than n cubed. So 1 over n cubed plus 1 is less than 1 over n cubed. And also this is bigger than 0. And as the sum from n equals 1 to infinity of 1 over n cubed converges, give me a little explanation that tells me you know why. It's a p series with p equal to 3. The sum from n equals 1 to infinity of 1 over n cubed plus 1 converges by direct comparison. Now you should use limit comparison when proving that the inequality goes the way you need it to go, for direct comparison is either difficult or just impossible. And so since those are kind of hard to distinguish, if you are not positive you can make your inequality go the way you want it to, use limit comparison. So we're going to use limit comparison. We're going to let the a sub n's be the terms in our series. We're going to let the b sub n's be n over the square root of n to the 4th, which will be 1 over n once we've simplified. So we're going to find the limit as n goes to infinity of a n over b n. So that's n over the square root of n to the 4th plus 1 times n over 1. This is the limit as n goes to infinity of n squared over the root n to the 4th plus 1. And now we multiply by 1 over n squared, 1 over n squared. The numerator is easy enough. That gives us 1. In the denominator, when that 1 over n squared goes into the root, it becomes an n to the 4th. This gives you 1 plus 1 over n to the 4th, and that limit is 1. Now be careful not to confuse this with the ratio and root test. It's okay if the limit comes out to be 1 for the limit comparison test. The thing that has to happen is this has to be a number that's bigger than 0. And then both series do the same thing. So as the sum from n equals 1 to infinity of 1 over n diverges, it's a harmonic, the harmonic series, or it's a p series with p equals 1, the sum of the a sub n's also diverges. Now, be careful here. If you do not put on that sum sign, you are wrong because you're talking about a sequence, not a series. So if you want to talk about an infinite sum, you have to put the summation symbol, or you're not talking about the infinite sum anymore, you're talking about the sequence. After the comparison tests, we had the first test that allowed us to test a series that had negative terms, but they were terms that were negative in a very specific way. These were alternating series, so series where the terms flip-flop positive, negative, or negative, positive in a very predictable manner. And these introduced examples of series that had different kinds of convergence. We had conditional convergence. This is where the series converges, so the sum of the a_n's converges, but the sum of the absolute values does not. And absolutely convergent means that the sum of the absolute values converges. And this actually implies that the series itself converges. So a series that's conditionally convergent, a good example is the alternating harmonic series, -1 to the n over n. That series converges by the alternating series test, but if you take its absolute value, you get 1 over n, and the sum of 1 over n diverges. A series that is absolutely convergent could be anything that has positive terms. You know that it converges, but here's a slightly more interesting example. -1 to the n over n squared. If you absolute value those terms, you get a p series with p equals 2, which converges. So to determine whether these series are convergent. So technically, this first one is actually not an alternating series because the terms don't flip-flop positive, negative. So, but it seems like it could be convergent. The way we're going to prove this is a combination of comparison and proving absolute convergence. So first, notice that the absolute value of this stuff that's less than or equal to 1 over 1 plus 1.2 to the n, because cosine, once absolute valued, is less than or equal to 1. And if I drop that 1 from the denominator, this is less than or equal to 1 over 1.2 to the n, which is the same thing as 1 over 6/5 to the n, or 5/6 to the n. And as the sum from n equals 1 to infinity of 5/6 to the n converges, remember this is a geometric series with r equal to 5/6, then the sum from n equals 1 to infinity of the absolute values that converges. And so hence the original series converges absolutely. And if a series converges absolutely, it also converges. So technically that was the comparison test, and using the fact that absolute convergence implies convergence. Now for this next one, I'm going to need more space, but you can see that this is an alternating series because -1 to the n will cause these terms to flip-flop. So we have in part B, the sum from n equals 1 to infinity, -1 to the n, root n over n plus 1. We're going to use the alternating series test. And I'm going to let Bn be root n over n plus 1. So the first thing you should show is that the limit as n goes to infinity of the b sub n terms is equal to 0. So we have root n over n plus 1. Well, if we divide everybody by root n, we have 1 over root n plus 1 over root n, which is definitely 0. So check that condition off. And the next thing you need to show is that b sub n plus 1 is less than bn. And in other words, this is showing that the sequence of b sub n's is decreasing. And you can't just state that it is so, you have to actually prove it. And really the way to prove this is to use a derivative and to show that that derivative is negative, which implies that the function is decreasing, which means as the n gets larger, the terms get smaller. So we're going to let the function f of x be root x over x plus 1, and we're going to use the quotient rule to get its derivative. So that would be x plus 1 times 1/2 x to the -1/2. So low d high minus high. The derivative of the lower function is 1 all over x plus 1 squared. So that's x plus 1 over 2 root x minus root x all over x plus 1 squared. And now to simplify that, let's multiply this by 2 root x over 1 and 2 root x over 1. Okay, doing so, we will have x plus 1 minus 2x over 2 root x times x plus 1 squared, and I swear we're almost done. This is 1 minus x over 2 root x times x plus 1 squared. Now this expression is less than 0 so long as x is greater than 1. And because that's true, then you can say that the sequence of b sub n's are decreasing. So since the limit of the b sub n's is 0, and since the b sub n's are decreasing, that's all you need. Therefore, this series converges. By the alternating series test. And the alternating series test also had a pretty nice remainder estimate theorem. This said that the absolute value of the remainder was less than or equal to the next absolute value of the next term you left off. And well, in this case, that next term you leave off will be 1 over n plus 1 to the 5th, and you want to ensure that that is less than 0.0001. So then solve this inequality for n. 1 is less than 0.0001 times n plus 1 to the 5th. Dividing both sides, we get 10,000 is less than n plus 1 to the 5th. Taking the 5th root, we got about 6.3 is less than n plus 1. And so 5.3 is less than n. So n has to be bigger than or equal to 6. So as long as our n is bigger than or equal to 6, our sum will be correct to within desired accuracy. So we can estimate this using the sum from n equals 1 to 6, negative 1 to the n plus 1 over n to the 5th. Well, inputting our numbers, when we input 1, we'll have 1. When we input 2, we'll have minus 1 over 2 to the 5th. Input 3 plus 1 over 3 to the 5th, minus 1 over 4 to the 5th, plus 1 over 5 to the 5th, minus 1 over 6 to the 5th. And you can take that and put it in a calculator, and you get that this sum is approximately 0.97208. The next tests we learned were probably your favorite, the ratio and root tests. So these were based on a comparison to a geometric series. So to perform the ratio and root tests, find the limit as n goes to infinity of the ratio of the n plus first to the nth term. And just be pretty careful when you input that n plus 1. So that will give us negative 5 to the 2 times the quantity n plus 1 power, n plus 1 to the second, 9 to the n plus 1, that's the a sub n. Now dividing by an is the same as multiplying by its reciprocal. So n squared, 9 to the n over negative 5 to the power of 2n. So that's the limit as n goes to infinity. Negative 5 to the power of 2n plus 2 n squared, 9 to the n over n plus 1 squared, 9 to the n plus 1, and then negative 5 to the 2n. Now the negative 5 to the 2n will cancel, leaving us a negative 5 squared. The n squared will not go away, but the 9 to the n will cancel with this 9 to the n. The n plus 1 squared stays in the bottom, as does a singular 9. So now squaring, taking the absolute value, we have 25 over 9 times n squared over n plus 1 squared. And as n goes to infinity, this part goes to 1. So this limit is equal to 25/9. And well, you think, okay, geometric series diverges when the r is greater than 1. This r is greater than 1. Therefore, the series diverges. And tell me what test you use. By the ratio test. This next question's a bit tricky because it's a bit tricky what to do with that factorial-ish thing in the numerator that is only odd numbers. So here we go. Let's find the limit as n goes to infinity of the n plus first to the nth term. All right, so in the numerator, we have 1, 3, 5. And when you have the n plus first term, you have one more term than is in this nth term. So if you input n plus 1, we've got 2 times n plus 1 minus 1, which is 2n plus 1. Now notice that these terms are separated by by 2. So think about one term prior to that is going to be 2n minus 1. So just be aware that this 2n minus 1 is here in this, like inside those dots that I've got written down. 5 to the n plus 1 factorial, that's the a sub n plus 1. 5 to the n factorial over 1, 3, 5, up to 2n minus 1. Okay, so you've got 1, 3, 5, 2n minus 1, 2n plus 1, 5 to the n factorial, all over 5 to the n plus 1 factorial, 1 times 3 times 5 up to 2n minus 1. And a lot of stuff will cancel. Notice that all this goes away. The 5 to the n goes away, as does the n factorial, leaving us just an n plus 1 in the bottom. So we have the limit as n goes to infinity, 2n plus 1 in the numerator, and a 5 times the quantity n plus 1 in the denominator. And that limit is 2/5. And you think, okay, geometric series converges if the r is less than 1. Well, this is less than 1. Therefore, the series converges by the ratio test. And lastly, one application of the root test. For what values of x will this series converge? Well, this series will converge the limit n goes to infinity, the nth root, absolute value an, is less than 1. So the nth root of the absolute value of ln x to the n, this will equal the limit as n goes to infinity, the absolute value of ln of x, and that's just a constant, so that's just the absolute value of ln of x. This needs to be less than 1. And that means that -1 is less than ln of x, which is less than 1. And now if we e everything, e to the -1, must be less than x, which is less than e, or 1 over e is less than x, which is less than e. You could have also said that this is a geometric series with r equal to ln x, and will therefore converge if the absolute value of ln x is less than 1. So technically, this would mean that you don't actually have to test the endpoints because you know that geometric series diverge at those endpoints. If you did test the endpoints, so say you want to be extra certain, you say, okay, well, at x equals e, we'll do the easy one first, we get the sum from n equals 1 to infinity, natural log of e to the n. Well, natural log of e is 1, 1 to the n is 1. This is the sum from n equals 1 to infinity of 1. That diverges. Test for divergence. The terms don't go to 0. If you plug in x equals 1 over e, you have to observe that the natural log of 1 over e is negative 1. So you've got the sum from n equals 1 to infinity of negative 1 to the n, and that will also diverge by the test for divergence.